So we have PhD, physics PhD practice qualifying exam problem number 14, electricity and magnetism domain. So let's begin. A cold plasma has electron density n sub e. The electron mass is m sub e and the electron charge is negative e. Ignoring collisions, an EM wave propagates in the z direction. Okay, part A. Starting from Maxwell's equations and electron equation of motion, derive the dielectric function epsilon of omega. Part B, derive the dispersion relation. Part C, determine the plasma frequency. Part D, find the group velocity. Part E, for the frequency slightly above cutoff, derive the asymptotic expression for phase velocity. And Part F, interpret physically why propagation ceases below plasma frequency. Okay, so electromagnetic waves in conducting plasma. So for part A here, we could say a cold collisionless plasma has electron number density n sub e, and electrons have charge e and mass m sub e. Ions are assumed fixed because they are much heavier. So we assume a transverse electromagnetic wave propagates in the z direction, and E equals E naught e to the I parentheses kz minus omega t close parentheses. The electron equation of motion is m sub e, and then second derivative of x with respect to t equals negative e, capital E. For harmonic time dependence, our second derivative here, x respect to t equals negative omega squared x. So negative m sub e omega squared x equals negative e capital E. So x equals e over m sub e omega squared e. The dipole moment of one electron is p equals negative e x equals negative e squared over m e omega squared times e. And the polarization is p equals sub n sub e p equals negative n sub e e squared over m sub e omega squared e. So we define omega sub p squared equals n sub e e squared over epsilon naught m sub e. So epsilon sub r of omega equals 1 minus omega sub p squared over omega squared. So epsilon of omega equals epsilon naught times the quantity parentheses 1 minus omega sub p squared over omega squared. Okay, moving along to part B. Part B, we want to derive the dispersion relation. Okay, so for part B here, dispersion relation. Let's see what we have. For a transverse wave, we have this cross products here. Del cross E equals negative del squared. E, because the dot product of del and E equals 0. So from Maxwell's equations here, okay, del cross E equals the negative partial B respect to T. Del cross B equals mu naught partial D with respect to T. And taking the curl of Faraday's law, del cross parentheses del cross E equals that partial derivative respect to T of the cross product of del and B. So substituting for Ampere-Maxwell law, we get del cross parentheses cross product del cross E equals negative mu naught second partial derivative D with respect to T. So D equals epsilon of omega E, negative del squared E equals negative mu E of omega, second derivative of E with respect to T. So, excuse me, sorry. Del squared E equals mu naught epsilon of omega, second derivative of E with respect to T. And for E equals E naught e to the I, parentheses kz minus omega t, we have del squared E equals negative K squared E. And the second derivative of E with respect to T equals negative omega squared times E. So K squared equals mu naught epsilon of omega squared. So mu naught epsilon naught equals 1 over C squared. K squared C squared equals omega squared E sub R of omega. Substituting here, E sub R of omega equals 1 minus omega sub P squared over omega squared here. And then K squared C squared equals omega squared minus omega sub P squared. So we could say right here, omega squared equals omega sub P squared plus C squared K squared. Okay, moving forward now, what they wanted for part C. So that's for part C, they want the plasma frequency. So the plasma frequency here is omega sub P equals just the square root of N sub E squared over epsilon naught M sub E. And this is the natural collective oscillation frequency of electrons against the approximately fixed ion background. For part D, they want us to find the group velocity. So the group velocity from the dispersion relation, omega squared equals omega sub P squared plus C squared K squared. Differentiate with respect to K. So 2 omega d omega dk equals 2C squared K. From here, V sub G equals d omega dk equals C squared K over omega. And using here following C squared K squared equals omega squared minus omega sub P squared. CK equals plus or minus square root of omega squared minus omega sub P squared. We only take the positive value of that. So CK, we use positive square root of omega squared minus omega squared, omega sub P squared. So what we get here is our V sub G equals C over W times the square root of omega squared minus omega sub P squared. So V sub G equals C times the square root of 1 minus omega sub P squared over omega squared. So that's part D. Part E, they want us, for the frequency slightly above the cutoff, derive the asymptotic expression for the phase velocity. So letter E, so right here, let's see if this holds. Okay, so here, phase velocity near cutoff. So the phase velocity is right here, that V sub P equals omega over K. So that's omega over K. So we use K squared equals omega squared minus omega sub P squared over C squared. V sub P is C omega over the square root of omega squared minus omega sub P squared. So for V sub P, we're going to get C over square root of 1 minus omega sub P squared over omega squared. Okay, so now if we consider the frequency slightly above the cutoff, omega equals a W sub P of the quantity 1 plus delta. Sorry about that, delta. And that's for 0 is less than delta is much less than 1. So omega sub P squared over omega squared is 1 over quantity 1 plus delta squared. So if we use 1 plus delta to the negative 2, that's approximately 1 minus 2 delta, 4 small delta, 1 minus omega sub P squared over omega squared. That's going to approximate 1 minus the quantity 1 minus 2 delta, and that'll be 2 delta. So from there, what we could say is V sub P is approximately C over the square root of 2 delta, and also V sub G equals C times the square root of 2 delta. So near the cutoff, we have the following: V sub P approaching infinity and V sub G approaching 0. So the phase velocity, it exceeds C, but this does not violate relativity because signal and energy transport occur at the group velocity. Okay. And for part F, interpret physically why propagation causes below plasma frequency. So for propagation, the wave number must be real. K squared equals omega squared minus omega sub p squared over c squared. If omega is less than omega sub p, then k squared is less than 0. So we let k equal I kappa, and kappa equal the square root of omega sub p squared minus omega squared divided by c. The wave is going to become E of z comma t is approximately e to the negative kappa z, e to the negative I omega t, which is evanescent rather than propagating. So omega less than omega sub p implies no propagating transverse electromagnetic wave. Physically, below the plasma frequency, electrons have enough time to rearrange collectively and screen the electric field. So instead of carrying electromagnetic energy through the plasma, the wave is reflected or exponentially attenuated. Okay, so that's all for this problem. Thank you very much and have a great day.